Imagine that we have the opportunity to do the impossible, to journey not to distant stars, but into the deepest abyss of time. What would await us there, 1 billion years away from our world? Welcome, intrepid explorers of the past. Our journey today takes us to an era when our planet itself was barely recognizable. Imagine a world where the atmosphere is only just beginning to fill with life-giving oxygen. Before us lies a primitive Earth, its young continents slowly floating through oceans stained the color of iron, rust. There are no plants or animals on this planet yet. Only giant colonies of bacteria carpet the seafloor, lending fantastical hues to the shallow waters. Volcanoes tower over this landscape, spewing lava into the thick, suffocating atmosphere. The deeper we delve into the past, the clearer one simple truth becomes. Life is the story of the greatest struggle for survival the universe has ever known. From the simplest bacteria to the most complex organism, humans, all creatures have traveled an incredibly long path to find their place on this planet. Millions of years of evolution have created majestic giraffes, soaring eagles, and leisurely turtles. Every living being in this endless chain is of colossal importance, for it was they who became the stepping stones to the astonishing and magnificent biodiversity we see today. One of the most important acts of this great drama unfolds in the geological eon in which we now find ourselves, the Proterozoic. Our goal is to peer into its final era, the Neoproterozoic, and see the world as it was 1 billion years ago. The word Proterozoic itself comes from Greek and translates as before animals. Scientists once truly considered this period a lifeless desert. However, today we know that this is not entirely true. The first animals were already taking their tentative steps across the planet during the Proterozoic, at least in its final Neoproterozoic era. And the Proterozoic never ceases to surprise. Every year, new research reveals ever more astonishing glimpses of the past. Our knowledge, supported by ever-evolving technologies, allows us to peer into previously inaccessible places and confirm the boldest hypotheses about the origins of life. 1 billion years ago, life was only just gaining momentum. We are now in the third part of the Proterozoic, which is divided into the Paleoproterozoic, the Mesoproterozoic, and finally the Neoproterozoic, which is of particular interest to us today. This period began 500 million years before the famous Cambrian Explosion. Before the Neoproterozoic era, the only life forms on Earth were microscopic but incredibly resilient bacteria and archaea. These organisms were true masters of survival, capable of adapting to the most extreme and harsh conditions. It's worth noting that at that time, food sources as we know them were virtually non-existent on the planet, and the very concept of hunting with teeth and claws had not yet emerged. And yet, despite the harshness of the environment and the complete absence of familiar food, life not only emerged but also seemed incredibly stable. It was so resilient that it continued to evolve, acquiring ever new forms. Let's travel back to the final days of the Mesoproterozoic era, before it gave way to a new, more advanced era, to understand how this ancient world evolved. Among the most astonishing early life forms were cyanobacteria, organisms destined to play a pivotal role in shaping our planet and its atmosphere. Their colossal significance to Earth's history is well studied, and we can precisely date their appearance thanks to the stone signatures they left behind. Stromatolites. These are fossilized rocks of biological origin, the oldest of which are over 3.4 billion years old. These amazing creatures reigned supreme among marine flora and fauna throughout the Precambrian period, from approximately 3.5 billion to 500 million years ago. Billions of years ago, the first living organisms, bacteria and cyanobacteria, emerged on our planet. Amazingly, even today, in some corners of the Earth, such as Australia's national parks, you can still see vibrant colonies of cyanobacteria, continuing to build their reefs of limestone and silica. We'll soon explore in more detail why these tiny creatures are so important to the entire history of life. But we can already say they began to oxygenate the planet's atmosphere. These bacteria, also known as chlorophyll bacteria, gradually transformed the atmosphere, triggering a true planetary revolution. And this revolution was absolutely necessary, because without it, the biodiversity of the animal world we know today simply would never have emerged. Just think. At the origin of all this potential stood a tiny bacterium. Indeed, for most of the Proterozoic, the first living organisms remained single-celled and fairly simple. But toward the end of the era, dramatic changes occurred. During the Neoproterozoic, life took another incredible leap. Complex organisms finally arrived on the scene. And here we are, a billion years later, in the Neoproterozoic. By the end of this period, most life forms were still single-celled, but multicellular creatures were already timidly making their presence known. Moreover, paleontologists have discovered traces of multicellular organisms dating back a whopping 2.1 billion years. As you can imagine, the various creatures of that era needed millions upon millions of years to adapt to the world and alter their genetic code for survival. This was the primary vector of evolution. The formation of a nucleus in a cell, or cellular specialization, became key breakthroughs of that time. This cellular diversity enabled the emergence of entirely new organisms, which, in turn, began to create new ecological niches. Thus, step by step, an entire ecosystem was born. Among simple organisms, we can observe the development and evolution of multicellular forms. For example, we already see algae diversifying, that is, separating into different species. These first steps toward complexity paved the way for the emergence of other life forms closely related to them. The butterfly effect, or domino effect, takes on a special planetary significance here. New species create new niches, and these niches, in turn, lead to the formation of new species, until a truly complex ecosystem emerges. An ecosystem in which all species are intimately intertwined with each other and their environment. The richness of this new system will stimulate the emergence of even more advanced organisms in subsequent eras. During the Tonian period, the first part of the Neoproterozoic era, which lasted from 1 billion to approximately 720 million years ago, numerous microscopic fossils were discovered, allowing scientists to gain a deeper understanding of this crucial period in the history of our planet. This was the beginning of a veritable explosion of evolutionary creativity in the history of life. Acritarchs appeared, creatures that we still cannot classify into any specific biological group. And in Australia, evidence of sexual reproduction in ancient fungi and green algae was found. Vertical burrows were discovered on Australian soil 800 million years ago. The scientific community, having studied these traces, concluded that they were likely created by worm-like creatures, possibly distant relatives of modern annelids. More complex life forms emerged in the second half of the Neoproterozoic era, a period named the Cryogenian, after the global glaciation our planet experienced. While microscopic life grew, some scientists speculate that they also discovered other primitive forms, such as sponges. These sponges began to form numerous marine rocks, such as spiculites. At the end of the Precambrian, the era preceding the emergence of complex multicellular organisms, new life forms emerged in aquatic environments. This was a turning point. The world of bacteria gave way to the world of eukaryotes, a world of organisms with a far more complex structure. However, to meet them, we still have several steps to go back in time. How did these first animals adapt to life on Earth? What incredible challenges did they have to overcome on their path to success? Let's return to the beginning of this period, to the Thonian. To understand the changes occurring in the living world, we must first take a close look at the planet itself, where these creatures evolved. In those distant times, the Earth was not divided into 7 continents as it is today. Everything looked completely different because from the planet's very birth, its surface was in constant motion. This process can be compared to a giant puzzle whose pieces continue to shift to this day. Tectonic plates are like giant pieces of a mosaic covering the surface of our planet. When we think of a single continent, the first thought that comes to mind is probably Pangaea. This is not surprising, as in our minds, this supercontinent is inextricably linked with dinosaurs, symbols of an ancient era. However, our planet has witnessed many monumental events beyond Pangaea. The history of plate tectonics is believed to span over 4 billion years. During this time, plate movement has regularly led to colossal changes in the planet's appearance. This continental waltz has played out repeatedly throughout Earth's history. Continental masses would sometimes converge, forming gigantic supercontinents, only to drift apart again, driven by tectonic processes. Our planet, to be precise, has experienced at least 7 such cycles. Imagine this creature floating in the depths of ancient water. Its enormous body wasn't just ballast. It acted as a gigantic stabilizer, like a ship's keel, allowing it to maneuver confidently, dampen the roll, and withstand collisions with underwater obstacles. These Paleoceans, as we see, were far from deserted. On the contrary, they teemed with life, even though even the most formidable sea monsters had not yet reached titanic proportions at the dawn of their evolution. And then, in a single geological moment, everything changed. An event scientists call the Cambrian Explosion took place, an unprecedented surge in species diversity. It was at this moment that the foundations of all the modern ecosystems we know today were laid. And most astonishingly, the biological richness of the marine flora and fauna of that era has come down to us in the form of exquisitely preserved fossils. To see this firsthand, we must travel to the southwest of modern China to Yunnan province. Here, in a place called Chengjiang, unique geological strata are found, renowned throughout the world. The fossils here are a true miracle, preserving not only the hard shells, but also the delicate soft tissues of ancient creatures. The Chengjiang fauna appeared immediately after the so-called small shell fauna, marking a new turbulent chapter in the history of life. Approximately 520 million years ago, previously unseen forms were born here. One of these key sites is Meitianshan Hill, which has been protected as a UNESCO World Heritage Site since 2012. It was on this hill in 1984 that Dr. Hou Xiangguang, a researcher at the Nanjing Institute of Geology and Paleontology, made a discovery that stunned the scientific world. What he found exceeded all expectations. It was a veritable Noah's Ark of stone, fossils representing 16 different animal phyla, more than 170 genera, and over 200 unique species. Here, we had the first glimpse of most of the animals that would dominate the planet in subsequent eras. Many of their descendants still inhabit our planet today. Among these rocky remains were the first algae, sponges, brachiopods, arthropods, and echinoderms. But this list is far from complete. Among this diversity were some true oddballs. One of the most studied and bizarre specimens is Hallucigenia. Imagine a tiny multi-legged worm that initially baffled scientists. Its fossil was so perfectly preserved that it allowed us to discern the smallest anatomical details. This creature had an oval head attached to its cylindrical body by something resembling a neck. At just 22 millimeters long, less than an inch, it had 7 pairs of slender limbs. The Chengjiang fauna also contains other fascinating creatures. For example, another unique creature lived here, an arthropod whose back was covered in sharp spines and whose 7 pairs of legs ended in tiny claws. Today, this animal is classified as a member of the lobopod group. One of the most striking representatives of this fauna is the prolific arthropod Fuxianhuia, whose remains have also been preserved in excellent condition. It is easily recognizable by its elongated, segmented body and, most importantly, by the 2 enormous appendages on its head. Each of these appendages bore 3 sensory antennae approximately 2 centimeters long. Another common creature that left behind numerous details for study is Unanozone intermedius. This trilobite-like organism possessed thin antennae on the front of its head, Its large crescent-shaped eyes framed a rounded head, which in turn ended in two long spines. Its rear end extended into a long, needle-like tail. However, the most famous fossil find from Chengjiang is undoubtedly that of Milokunmingia fengjiawa. Why is it so important? Because we are looking at what may be the oldest known vertebrate, our distant ancestor. It was a tiny primitive fish, only about 2.5 centimeters long. Its head was already clearly separated from its body, and 5 to 6 gill slits were located on each side. Its body likely had dorsal and pelvic fins that merged into a single band. Its muscular system consisted of 25 V-shaped segments, and although the details of its mouth are not yet fully understood, it already had a fully developed digestive tract that extended to the very tip of its tail. But in any world where life exists, a predator emerges sooner or later, and in the Cambrian seas, this predator was a true monster. Its name was Anomalocaris, which translates as strange shrimp. This nightmarish predator from the extinct family of radiodonts could grow up to a meter in length, the size of a titan for that era. Its front end was armed with 2 large, segmented and incredibly prehensile appendages studded with spines. Its head was crowned with 2 enormous eyes on long stalks, and at the bottom was a terrifying round mouth, resembling a hole saw. This creature's segmented body bore 11 pairs of paddles, which likely made it an excellent swimmer. With such an arsenal and its keen eyesight, it easily hunted trilobites and other prey. Scientists estimate that in this complex ecosystem, over 55% of the species were arthropods, about 10% were sponges, and another 10% had such a bizarre anatomy that their classification is still debated. Most of these creatures crawled along the ocean floor, and only a few, like Anomalocaris, were active swimmers, as their anatomy prevented them from even passively hovering in the water column. Feeding strategies were extremely diverse. Some filtered water, others absorbed silt, still others scavenged, and still others, the most formidable, were active predators. The Chengjiang finds provide irrefutable proof. The Cambrian Explosion is not a beautiful theory, but a harsh reality. The diversity of life during this period was truly astonishing, as many previously unseen groups of organisms emerged in a short geological time span. Some of them survived this era and gave rise to new dynasties, while others disappeared without a trace. But it was this period that became the cradle of all the complex forms of animal life we know today. But the history of life did not unfold linearly. During the early Cambrian era, there was another brief but significant period that gave rise to the so-called Tomot fauna. Named after the Siberian city of Tomot, it emerged approximately 530 million years ago and lasted only a few million years. Although not as famous as the Ediacaran fauna, this fauna is of great interest to paleontologists. It is often called the small shell fauna, and for good reason. Most of the finds are tiny lobes, tubes, spines, caps, and domes of minerals. The nature of this fauna remains a mystery to scientists. What were they? Were they simply scattered fragments of the very first armor, which had not yet fused into a single shell on unknown organisms? Or are they the remains of mosaic armor that covered the bodies of previously known but poorly preserved animals? Or perhaps these strange finds are all that remain of unique creatures that appeared and just as quickly disappeared. Until recently, it was believed that the Tomot fauna was the first to develop hard shells. However, recent discoveries of more ancient organisms with mineralized skeletons have disproved this theory. The Tomotian epoch is significant for another reason. It marks the emergence of a group of organisms known as Archaeochyatha, a distinct class of extinct sponges. Although this group disappeared at the end of the Cambrian, Archaeochyatha were among the planet's earliest bioengineers. Teeming with calcifying microbial communities, they created gigantic organic masses up to 2 meters high and several meters in diameter. These calcareous sponges decorated the seafloor, creating previously unseen landscapes. These massive organisms became the precursors of the complex reef ecosystems that would flourish only millions of years later in the Ordovician period. All that remains of the Tomotian epoch are these mysterious traces in history. But let's return to the giants. We've already met Anomalocaris, the apex predator of the Cambrian seas. This strange and incredibly large shrimp, reaching a meter in length, wasn't alone in its hunt on the ocean floor. Just recently, in June 2022, scientists introduced the world to another prehistoric leviathan, a giant arthropod from the radiodont group. It was named Tectonic guinesi. Its remains were discovered in the famous Burgess Shale Formation in British Columbia, Canada. The very name of this creature, a reference to the Titans, speaks of its exceptional size. The suffix "coris" means helmet in Greek. Reaching half a meter in length, this animal was incredibly huge for its era. Today, this may seem modest, but let's fast forward to 500 million years ago. In a world where most living creatures were the size of a finger, Tectonic was a true titan. Most of its contemporaries were 5 times smaller, with the possible exception of its relative Anomalocaris. Like other radiodonts, Tectonic guinesi stood out for its exceptionally long body, but its most striking feature was its head, covered in a massive 3-part shell of varying shapes. This head was so disproportionately elongated relative to the rest of its body that it gave it a completely alien appearance. Imagine a creature whose head was so disproportionately large relative to the rest of its body that some paleontologists jokingly nicknamed it a floating head. Its mouthparts were a terrifying conical structure composed of several radiating plates, each studded with needle-sharp teeth. Above this deadly crown rose its eyes, mounted on flexible, multifaceted stalks, like the periscopes of an ancient predator. 2 long anterior appendages, armed with powerful claws, pointed backward, ready to seize unwary prey at any moment. The body itself consisted of numerous flexible lobes, which undoubtedly facilitated graceful yet deadly swimming, and also supported its gills. This veritable colossus, whose outer shell was wider and thinner than that of the average radiodont, preferred to stay close to the seafloor, patrolling coastal waters. It is safe to say that it was one of the most dangerous predators that the oceans faced during the Cambrian era. On the other hand, not all of its relatives were such bloodthirsty giants. Smaller radiodont species, although similar in body structure, chose a completely different survival strategy. They were peaceful filter feeders, sifting the water in search of plankton. This was the key to their coexistence. While the titanic radiodont stalked larger prey, its smaller brethren were of no interest to it, quietly occupying their ecological niche. The study of unique paleontological finds, such as the Chengjiang Formation, the Burgess Shale, and numerous other fossil-rich sites, allows us to state with complete certainty. At the beginning of the Cambrian period, a highly complex marine ecosystem was emerging before our very eyes. The world of living organisms that preceded this famous Cambrian explosion was already distinguished by significant diversity. It included several evolutionary lineages, each of which adapted in its own way to mastering its environment. However, the anatomical structure of these early creatures was still relatively simple. The Cambrian period witnessed not just an incredible proliferation of life, but a genuine quantum leap. At this point, fundamentally new anatomical and functional structures emerged, an order of magnitude more complex than anything that had existed before. Regarding sensory organs, evolution gave living creatures eyes and sensitive antennae, allowing them to better navigate. Many organisms developed fully functional gills and a circulatory system, evidence of true respiration. For food acquisition, complex digestive tracts emerged. Some animals developed sophisticated systems for capturing tiny food particles, and predators even acquired specialized grasping organs. Finally, in terms of locomotion, we see a real breakthrough. A whole variety of appendages and swimming organs appeared. The impressive appendages of arthropods, some of which would later give rise to such thriving groups as crustaceans, are undeniable. All these new anatomical features led to a radical increase in the complexity of the entire marine ecosystem. Animals were no longer simple single-celled organisms like prokaryotes or eukaryotes, or even primitive multicellular organisms like some myxobacteria. They now possessed a whole arsenal of specific organs that clearly defined their place in the new world. The discovery of organisms with a wide variety of body plans indicated that the food chain was already well structured. Indeed, we find traces of preapulid worms in the sediments, see a multitude of arthropods that inhabited the seafloor and encounter true apex predators that inspire fear, such as the famous Anomalocaris. However, studying the anatomy of these creatures, frozen in stone for millions of years, is not the only key to understanding their lives. In some deposits, scientists were incredibly fortunate. They were able to analyze stomach contents and even coprolites, fossilized excrement of some specimens. Observing the fossilized food in their stomachs and the remains of their final meal in their intestines provided a remarkably accurate picture of the diet of these ancient animals. This made it possible to state with absolute certainty that certain species preyed on others. Stomach contents provide direct, irrefutable evidence of predator-prey interactions in the food chain. Several organic and skeletal fragments preserved in the stomachs or intestines of several animals were discovered in the famous Burgess Shale. The priapulid worm Otoya apparently preferred to hunt hyoliths. Perfectly preserved shells of these enigmatic creatures were found in its digestive tract. The arthropod Cydnea, however, had a far more varied menu. Numerous fragments of hyoliths, trilobites, and small arthropods were found in its digestive system. This voracious predator, reaching lengths of 5 to 16 centimeters, was a real terror for small seafloor dwellers. But the scientists didn't stop at studying the digestive tracts. Among the fossils examined were those that could have been ancient excrement. These potential fossil feces came in a variety of shapes. Some were elliptical and consisted of entire clusters of skeletal remains belonging to the Chengjiang fauna. They turned out to primarily contain fragments of Waptia and Bracharites, the smallest arthropods that inhabited the seafloor. But what could have ended this thriving world? It's plausible that some external force, such as a giant meteorite impact or a nearby supernova, could have caused the catastrophe. This could have been the final chord in this great drama. In just 10 seconds, the planet's protective shield, the atmospheric ozone layer, would have been completely destroyed. Oceanic plankton, the foundation of the entire food chain, would have lost their protection from harmful ultraviolet rays. A new ice age would gradually set in, encasing the supercontinent Gondwana at its south pole in a vast ice cap. Due to a sharp drop in sea level and a slowdown in ocean circulation, oxygen levels in the water would have plummeted, leading to much harsher, unbearable conditions for life. Thus, the Cambrian Era came to a tragic end, culminating in a mass biological extinction known as the Cambrian Ordovician extinction. Brachiopods, conodonts, and the famous trilobites suffered the most from this catastrophe. But, as always happens in such situations, surviving species have a chance to occupy the vacant spaces. Ecological niches are empty, and nature demonstrates its amazing, inexhaustible resilience. Despite a seemingly uninviting and hostile environment, life continues to evolve and flourish once again. In the calmer waters of a renewed ocean, life returns to its usual course. Survivors reproduce vigorously, and new, amazing species appear on the scene. Planet Earth seems to be at the peak of its development at this moment, and this raises an intriguing question. Will life, which originated in the water, soon dare to take the next most daring step, spreading onto land? And if so, will the next period in the evolution of species be even more spectacular? Right now, we are experiencing the transition from the Cambrian to the Ordovician period, a new, colder era in Earth's history. As a result of this transition, the planet's oceans and atmosphere are cooling significantly, setting the stage for the next act in life's great drama. Throughout its long and turbulent history, planet Earth has known several gigantic supercontinents, veritable titans of rock and earth. Let's travel back in time, to an era billions of years away. Paleontologists believe that the fourth supercontinent, named Columbia, began to form approximately 1.8 billion years ago. Unfortunately, we know disappointingly little about this ancient world. Time is the greatest destroyer. In the hundreds of millions of years that have passed since then, almost all traces of this monumental period in Earth's history have been erased from its surface. Our knowledge is still fragmentary, and we cannot recreate with complete certainty a picture of that crucial stage in the life of our planet. However, we do know one thing. After tens of millions of years of existence, the colossal Columbia began to crack at the seams and disintegrate. But this disintegration was only a prelude to a new unification. Like giant puzzle pieces drawn by an invisible magnet, the enormous land masses rushed toward each other again. Thus was born the first truly well-studied supercontinent, Rodinia. According to researchers who have dedicated their lives to studying this era, Rodinia was a true melting pot. It consisted of many familiar fragments. Here was the ancient continent, which scientists call Laurentia, the core of what would become North America. Adjacent to it was the Baltic, the foundation of Eastern Europe. But this was only the beginning. This grand union also included what would become Amazonia, West Africa, and even distant Australia. Millions of years passed, and Rodinia, in turn, succumbed to the internal stress and fractured. A new continent emerged from its ruins, Pinotia, also known as Gondwana, or Pan-African. The name speaks for itself. At the center of this new world lay the African plates. And finally, the last in this parade of giants is the supercontinent Pangaea. It is undoubtedly the most famous of them all, as it is the closest in time to us. Its history is well documented in stone, and it is inextricably linked with the age of dinosaurs, whose glory has not faded even tens of millions of years after their demise. Yes, that unique world that became home to these incredible creatures from another era is, of course, Pangaea. It finally formed around 335 million years ago, and its great breakup began in the Jurassic period, approximately 175 million years ago. But now that we've refreshed our memory of this geological timeline, let's return to the main character of our story today, Rodinia. This supercontinent arose in the Neoproterozoic Era, between 1.1 and 0.9 billion years ago. Imagine this scene. Colossal landmasses drifting across the planet finally collide and merge into a single monolithic space. Scientists have named this world Rodinia, which translates from Russian as motherland, a place where something new was born. This unique landmass was located in a rather unusual location, at the 60th parallel north, yet not far from the South Pole. The average temperature on its surface was quite cool, around 10.5 degrees Celsius, and this entire landmass was surrounded by a single, boundless global ocean known as Morovia. And while life was already teeming in the depths of this ocean, a completely different, lifeless picture reigned on land. Amidst the endless dust, rocky deserts, and craggy chaos, it was impossible to find even a corner for life. The first thing that would strike a modern observer is the complete, absolute absence of plants, not a single tree, not a bush, not even a blade of grass. If today deserts seem exotic to us, occupying only a fraction of the planet, then imagine that in those days, a similar lifeless landscape covered almost the entire land. Only on the coast, at the very edge of the water, were barely noticeable changes taking place. Life in the form of primitive plant organisms was already creeping toward the shore, but it was still hundreds of millions of years before they would conquer the continent. For now, all life was locked in its aquatic cradle. At this moment, the entire drama unfolded underwater. The oceans and seas, which covered most of the planet, were destined to play a key role in the coming geological transformations. They became the environment where the first organisms that learned to produce oxygen emerged. It was here that countless species would thrive, evolve, and prepare to emerge onto land. However, the inexorable movement of tectonic plates was preparing their first serious test, the consequences of which were felt even on the surface. During the Proterozoic Era, plate tectonics was particularly turbulent. This internal turmoil of the planet inevitably led to colossal changes on the surface. As a result of plate collisions, gigantic mountain ranges arose. Scientists call this process orogeny, the birth of mountains. Several such events occurred during that period. We are interested in the time period approximately 1 billion years ago, when two main mountain building scenarios unfolded. The first is the so-called Grenville orogeny, which was a direct consequence of the breakup of Columbia and the subsequent formation of Rodinia. Several million years later, at the end of the Neoproterozoic, new mountain ranges emerged on the planet, the Khoton and Pan-African Mountains. Throughout this era, incessant volcanic eruptions were a clear indication of the Earth's incredible internal activity. The fiery heat and energy stored within its depths had to find a release, otherwise our planet simply would not have withstood such pressure and would have torn itself apart. It was a time of a grand dance of continental plates, violent eruptions, and massive mountain building. The Earth's landscape was transformed beyond recognition. Stone monuments rose on its surface, seemingly propping up the sky itself. The supercontinent Rodinia, unable to withstand the strain, began its slow death. Volcanism and continental shifts continued to carve and reshape the planet's surface, altering its geography. The face of the Earth changed, new mountain ranges formed, oceans retreated, and vast tracts of land rose in their place. Rodinia, once a unified and powerful continent, gradually disintegrated into 8 separate fragments, like a gigantic mosaic scattered by an invisible hand. These massive movements of the Earth's crust were merely a reflection of what was happening deep within our planet. There, in the depths, chaos reigned. Rocks melted, turning into a viscous, superheated liquid that carried excess heat to the surface, and the Earth's crust, like splinters on the surface of this fiery torrent, shifted, cracked, and tore. And this rupture of Rodinia would lead to the birth of a new, previously unseen element on the world map. There's a place on our planet that many of us dream of, but in those distant times it simply didn't exist. It's the Pacific Ocean. First, Rodinia split into 2 enormous pieces. On one side was what would become Australia and East Antarctica, and on the other was Laurentia, which included North America and Greenland. A giant crack, a depression, appeared between them, which over time turned into a massive crustal fissure. We would have seen violent volcanic activity in this rift. Gradually, the waters of the world's oceans began to penetrate it, and the rift became a full-fledged oceanic ridge. This new ocean was nothing less than the ancestor of the Pacific Ocean, or, more accurately, the Panthalassa Ocean, of which the modern Pacific Ocean is a part. We could also call it the Proto-Pacific Ocean. The term Panthalassa itself is more often used when referring to the future supercontinent Pangaea, which was washed by this gigantic ocean and had a vast gulf called Tethys. Either way, it was then, between the future Australia, Antarctica, and North America, that the famous ocean, now one of the most beautiful and majestic on our planet, began to form. 1 billion years ago, Earth experienced another turning point. The planet began rapidly becoming saturated with oxygen. At first glance, this might seem like great news. But for billions of organisms that had been accustomed to living in an oxygen-free environment for centuries, this was a true catastrophe. For some living beings, this new gas and its growing abundance meant chaos and death, but for others, it was an incredible opportunity for evolutionary leaps and the blossoming of exceptional diversity. Let's go back a few million years to better understand this new feature of our planet. Almost immediately after its birth, Earth already had an atmosphere, but it bore little resemblance to the one we're accustomed to. We're talking about a primitive atmosphere that existed 4.6 billion years ago and consisted primarily of carbon dioxide, nitrogen, and water vapor. But how can we know this? How can we be sure of the composition of air from such a dizzyingly ancient time? Dating the remains of animals or plants is no easy task, but how can we determine the presence of a simple gas billions of years ago? 4.6 billion years is a period of time our brains can barely comprehend. An unimaginable number of events have occurred during this time. However, ancient rocks are coming to the aid of scientists. Studying fossils, and especially tiny gas bubbles trapped within rock, and zircons, incredibly durable minerals that can survive millennia, helps us understand how the Earth's atmosphere formed and changed. These minerals are invaluable witnesses to history, true time capsules that tell us about ancient eras. Armed with the necessary knowledge and tools, we can confidently peer into those distant times. Today, we know that the primordial atmosphere consisted of carbon dioxide, nitrogen, and water vapor. Everything could have remained this way, but one tiny grain of sand in this complex system led to irreversible changes. The consequences of these changes were devastating for some life forms, but a true blessing for others. The primeval Earth gradually cooled and the hot water vapor condensed, turning into boundless oceans and rivers. And as you already know, about 3.5 billion years ago, life arose in this aquatic cradle, particularly with the emergence of cyanobacteria. These microscopic creatures became the basis for all future diversity and literally turned the familiar world upside down. As they saturated the ocean and atmosphere with oxygen, these two environments became acidifying, something never seen before. In the very beginning, bacteria, known as autotrophic prokaryotes, produced oxygen, which immediately reacted with various chemical compounds on the Earth's surface. These compounds, methane, salts, and iron minerals, acted like a giant sponge, soaking up free oxygen. Scientists call them oxygen absorbers. However, after millions of years, these sponges became completely saturated. They were completely oxidized and could no longer absorb oxygen. It is believed that they reached saturation point, and then, approximately 2.45 billion years ago, oxygen began to be released in huge quantities into the water and atmosphere. This event, known as the oxygen catastrophe, was a death sentence for anaerobic prokaryotes. Imagine their own environment suddenly becoming toxic. Imagine the horror of a living creature, not gaining life with every breath, but suffocating, dying in agony, tirelessly searching for the gas that linked it to life, but finding none. And worst of all, this deadly poison was secreted by their neighbors, other bacteria, who, without realizing it, were committing the first mass genocide in the history of the planet. The world was plunged into suffocating chaos. Let's travel back in time, 2.5 billion years. Imagine an ancient ocean. Its waters were saturated not with life, but with dissolved iron. And now, into this primeval environment, a new aggressive gas invades, one that will forever change the face of the planet: oxygen. This collision triggers a massive chemical reaction, a veritable planetary process of rusting. Why are we talking about rust? Because its traces, frozen in stone, still capture the imagination and serve as irrefutable witnesses to those distant events. Look at these majestic rock formations, dotted with history. Do you notice those long, reddish-brown ribbons running through the rock? These are more than just pretty patterns. They are a geological record, the most important evidence of our deep past. These alternating red and gray layers are known as banded iron quartzites. Two billion years ago, when oxygen first reacted with iron, the resulting rust slowly sank to the bottom of the world's oceans, covering it layer after layer. And today, we find these imprints of time, which allow us to date with incredible precision one of the greatest events in Earth's history, the oxygen catastrophe. Chemically, the process was simple, but its scale was colossal. Water-soluble divalent iron, or Fe2+, washed from the continents into the ocean. There, it encountered oxygen and converted into insoluble ferric oxide, Fe3+. It was these particles settling to the seafloor that formed the very deposits we see today, not only in Michigan, USA, but also in various parts of the world: Australia, Brazil, India, Russia, and South Africa. These ancient formations are also known as paleosols, fossil soils formed by the weathering and erosion of continental rocks under the influence of a primitive atmosphere and water. Their characteristic blood-red color is due to the presence of hematite, an iron oxide mineral with the chemical formula Fe2O3. This simple formula clearly demonstrates the inextricable bond between iron and oxygen, which painted the ancient world in crimson hues. Returning to the marine sediments, we see alternating red and grey layers. While the red color is a result of iron precipitation, the grey hues are due to another substance: silica. Between 185 billion and 850 million years ago, during the era scientists call the Neoproterozoic, the oceans continued to actively produce oxygen. Gradually, it saturated not only the water, but also the land, and then began to leak into the atmosphere. This led to another planetary event, the formation of the ozone layer. As soon as we leave the ocean and ascend high into the atmosphere, oxygen appears before us in a new guise. Here, it becomes trioxygen, or, as we are accustomed to calling it, ozone. The ozone molecule is a compound of 3 oxygen atoms. At such a high altitude, it acquires the remarkable ability to absorb the sun's harmful ultraviolet radiation, which is deadly to all life. Thus, the ozone layer became a true celestial shield, a salvation for future ecosystems and all living things yet to emerge. The sun gives us beneficial warmth and light, but it can also incinerate all living things. There are 3 types of ultraviolet radiation: UVA, UVB, and UVC. These invisible rays can cause mutations in the very foundation of life, the DNA molecule. Even minor damage to this genetic material can have catastrophic consequences for an organism. This is why the formation of the ozone layer, located in the stratosphere, was so important. It became the protective shield that absorbs most of the deadly rays, providing reliable protection for the genetic code of life. The Neoproterozoic period marked a turning point in the history of our planet. Although oxygenation began millions of years earlier, it was the high oxygen content that marked the break between the early Proterozoic eras, the Paleoproterozoic and Mesoproterozoic, and the final Neoproterozoic era. About 1 billion years ago, oxygen became the dominant element, forever changing the rules of the game. If we analyze its concentration, we see a striking picture. About 2.4 billion years ago, its partial pressure was practically zero. Then, until about 1 billion years ago, it remained negligible, less than 1/10 of an atmosphere. And then, suddenly, between 900 and 800 million years ago, an explosive increase occurred. The pressure jumped to its maximum, exceeding 0.3 atmospheres. This new oxygen-rich atmosphere brought with it entirely new climatic conditions. The former world, shrouded in a dense methane haze, was significantly warmer than today. Imagine a planet with perpetual tropical temperatures and warm, sunlit seas, perfect conditions for the emergence of the first life forms. However, despite this seemingly favorable climate, believing in stability would be naive. While that era was marked by periods of intense heat, they were also followed by monstrous ice ages. During those times, the Earth would be completely covered in ice, turning into a giant snowball hurtling through space. Such cataclysms testify to incredibly complex and large-scale processes occurring on our planet. The Neoproterozoic era was a time of intense continental movements. The supercontinent Rodinia may have broken up into 8 separate landmasses. Such a global reorganization was bound to have consequences. A series of ice ages was undoubtedly closely linked to these tectonic and climatic changes. To understand how a phenomenon like Snowball Earth is even possible, we need to understand its mechanism. How can an entire planet turn into an icy desert, covering almost its entire surface? Forests, oceans, deserts, all are buried under kilometers of snow and ice. The key factor here is the atmosphere. It determines the quality of life, protects from radiation, and shapes the climate. And climate, in turn, is directly dependent on the Earth's radiation balance, the difference between the energy the planet receives from the sun and the energy reflected back into space by the oceans, land, and the atmosphere itself. This delicate balance is maintained by greenhouse gases. However, as we've already seen, a sudden influx of massive amounts of oxygen can disrupt this equilibrium, leading to serious consequences. The changes that began in the ocean inevitably affected the atmosphere as well. Some gases transform when they interact with oxygen. This is how ozone was formed. But we haven't yet discussed the fate of methane. Methane, reacting with oxygen, turns into carbon dioxide, a much less potent greenhouse gas. The planet, deprived of its warm methane blanket, begins to cool rapidly. Gradually, it becomes covered in ice. In places, it reaches a kilometer in thickness, encasing the entire planet. If you looked at Earth from space during this period, it would be unrecognizable. The amount of methane in the atmosphere declined, and with it, the temperature. But that's not all. Sudden temperature changes lead to the formation of ice, and this process, once started, only intensifies. To understand why this happens, we need to understand the albedo effect. Albedo is the ability of a surface to reflect sunlight. As the Earth becomes icier, and ice is the most highly reflective material, the temperature continues to drop exponentially. A monstrous chain reaction is triggered. More ice means more reflected light, means lower temperatures mean even more ice. For several million years, our planet resembled a giant white snowball orbiting the sun. This wasn't the first glaciation in history. During the Proterozoic Era, Earth experienced the formation of 4 supercontinents and 3 gigantic ice ages, which led to a series of dramatic changes. The first of these, the Paleoproterozoic glaciation, lasted from approximately 2.4 to 2.1 billion years ago. It was followed by the first mass extinction, known as the Huronian. During the Neoproterozoic, the final era of the Proterozoic, Earth experienced 2 successive glacial apocalypses. The first, known as the Sturian glaciation, was global in scope and occurred during the Cryogenian period. Scientists estimate it lasted approximately 57 million years, between 717 and 60 to 60 million years ago. This period was undoubtedly the most dramatic, both in its intensity and duration. The same can be said of the Merino glaciation, which occurred several million years later, also during the Cryogenian period. It lasted from 650 to 635 million years ago. Despite its shorter duration, this glaciation was incredibly severe. Once again, ice covered virtually the entire planet. Depending on the region, the world's oceans could have been frozen to a depth of several kilometers. Studying glacial deposits from that period, scientists conclude that it may have been the most intense glaciation in the entire history of our planet. But what could end this downward icy spiral? The answer lies not only in the Earth's depths, but in the air itself. The only mechanism capable of stopping the planet's total freezing is the greenhouse effect. It occurs due to the accumulation of carbon dioxide, which was continuously released into the atmosphere by volcanic eruptions. While the oceans were frozen, they could not absorb CO2, and it accumulated in the atmosphere. Once this process reached a critical point, the greenhouse effect began to warm the planet's climate. The ice began to melt. Slowly but surely, after millions of years of icy captivity, the Earth began to awaken. After millions of years of icy imprisonment, the planet is finally beginning to thaw. The global winter is retreating, and in its place are milder, more forgiving temperatures, which once again make it possible for life to flourish, both in the oceans and on the barely forming landmass. This process is accompanied by massive cataclysms. Entire chains of volcanoes erupt, the Earth's interior churns with colossal internal activity, and molten gases burst forth from cracks in the crust. And all of this is part of a single chain, evidence of tectonic shifts occurring deep beneath the surface. Once the Earth sheds its icy shell, the famous snowball will become a thing of the past. Our planet will shed its centuries-old shroud and return to more comfortable conditions for life. As a result of this great warming, gigantic masses of snow and ice begin to melt, rushing into the world's oceans and bringing with them unprecedented quantities of nutrients. This has become the impetus, the catalyst, for the explosive proliferation of new species, which immediately rush to occupy the vacated ecological niches. Although life remains concentrated exclusively in water, after a period of ocean oxygenation and subsequent global cooling, we witness the emergence and rapid development of a whole kaleidoscope of living organisms. A world of ancient algae, primitive sponges, and the astonishing Gabonionta unfolds before us. These Gabonionta are creatures that lived approximately 2 billion years ago. They were macroscopic, meaning visible to the naked eye, and belonged to the first multicellular groups, although they were not yet eukaryotes. Their bodies had a bizarre shape, reminiscent of a pleated skirt gathered around a central disc, and their tissues were soft and gelatinous, very similar to the flesh of modern jellyfish. At that time, several species of these mysterious creatures already inhabited the oceans. By studying fossilized sediments, paleontologists are finding traces proving that these organisms were capable of slowly moving along the ancient seafloor. The very possibility of such complex multicellular organisms opening up entirely new horizons in our understanding of the evolution of life on Earth. It was a true breakthrough, creating countless opportunities for the development of a wide variety of life forms. And although scientists doubt that the Gaboniontes left direct descendants several hundred million years later, between 1.7 and 1.2 billion years ago, new multicellular players appeared on the scene, red algae. They replaced the so-called blue-green algae, or cyanobacteria, which had previously dominated the oceans. The oldest fossils of red algae were discovered in the Vindhyas Mountains in India. They are estimated to be an incredible 1.7 billion years old. These pioneers of the plant world, members of the Rhodophyta family, were able to take advantage of the new conditions created for them by their predecessors, cyanobacteria. This included increased atmospheric oxygen levels, but even with this advantage, life remains a constant battlefield. Although large predators were not yet nearby, the environment itself was harsh and hostile, seriously limiting their opportunities for development. Our red algae had to adapt to this harsh world. They faced two problems at once: a lack of sunlight at depth and ever-increasing oxygen levels in the water, toxic to many life forms. In response to this challenge, evolution suggested a solution: moving closer to the surface to access the sun's saving rays. This maneuver was made possible by the formation of the ozone layer, which, like an invisible shield, protected living organisms from deadly ultraviolet radiation. As we recall, this protective layer emerged precisely due to the accumulation of oxygen in the atmosphere. However, the algae couldn't rely on photosynthesis alone, using chlorophyll. Even as they ascended, they remained at considerable depths, where only dim, diffused light penetrated. To survive in these twilight conditions, they developed a unique mechanism. Their cells developed additional pigments capable of capturing those frequencies of the light spectrum that chlorophyll couldn't absorb. These protein pigments, with a pinkish tint, give the algae their characteristic red color. Thanks to this remarkable adaptation, they learned to effectively capture even the weakest rays of solar energy and convert them into organic matter. During this same period, even more complex and diverse organisms appeared in the oceans. It seemed as if life itself had decided to conduct a grand experiment. After the age of algae and mysterious gabonionts, metazoans entered the scene, the first creatures we can rightfully call animals. Their structure underwent revolutionary changes. First, their cells became differentiated, that is, specialized, and began to unite into true tissues. Second, they developed a nucleus and mitochondria. the true powerhouses of the cell. This was a giant leap in evolution. And another key fact: these creatures were heterotrophs, meaning they did not produce their own food, but fed on ready-made organic matter. The first such multicellular animal known to science was, of course, the sponge. Researchers have discovered steroids, a special class of fats, in ancient rocks, indicating that sponges existed as early as 890 million years ago. Take a look at this amazing creature. Its entire structure seems designed for one purpose: filtering water. Although the sponge doesn't yet have clearly defined organs or tissues, its entire body is a complex filtration system for extracting food. Water enters through countless pores and moves through a system of channels. Some serve to distribute the flow, others to collect it. In biology, this is called an aquifer system. By forcing water through itself, the sponge is able to trap tiny particles, mainly bacteria, which become lodged within its cells. This process is called phagocytosis, where the cell literally engulfs particles less than half a micron in size. Then, enriched with nutrients, the sponge expels waste through the same channels, maintaining a continuous life cycle. To be strong and stable, any organism needs a skeleton. In sponges, this consists of silica or limestone. In the most ancient representatives of this family, we find microscopic calcite needles, or spicules, which form their calcareous framework. It was long believed that the oldest sponges were around 650 million years old, but recent discoveries are forcing us to reconsider this date, pushing it back almost 200 million years. Professor Elizabeth Turner of Laurentian University in Canada made a truly incredible discovery while studying ancient stromatolites. These layered formations, formed by photosynthetic bacteria, were found in the Pilbara region of Australia. Within them, scientists discovered a complex network of microscopic channels filled with pyrite, a mineral formed during the decomposition of organic matter. It was this structure that held the key. The study revealed that these were the fossilized remains of an ancient sponge, more precisely its skeleton, which created the image of a worm-like organism living within the stromatolite. But it wasn't a worm, but a sponge. After death, its soft tissue decomposed, but the mineralized skeleton preserved the very same network of tiny channels we discussed earlier. What makes this discovery so astonishing? First, we've discovered a species that's at least 890 million years old. This pushes the origin of animals back more than 200 million years. Second, it proves that sponges may have lived symbiotically with cyanobacteria, which created stromatolites. And finally, and most importantly, we know that oxygen appeared in large quantities much later, and that between 720 and 635 million years ago, Earth experienced a global glaciation, the so-called Snowball event. Two crucial conclusions follow from this. First, oxygen was not the only or necessary factor for the development of complex life. Second, this life existed in conditions we would consider absolutely unbearable today. It was resilient and adaptable enough to survive the ice ages that gripped the entire planet, and while subsequent ice ages undoubtedly led to a decline in the population of these first multicellular organisms, sponges have not yet had their last word. Even today, their descendants can be found in every corner of our oceans. They had a few more tricks up their sleeve. They witnessed countless events in the history of our planet: numerous evolutionary turns, global upheavals, climate changes, and renewals. This humble sponge allows us to glimpse the new world of eukaryotes. And speaking of renewals and upheavals, let's fast forward a few million years. We find ourselves in a new time period that concludes the Neoproterozoic Era. This is the Ediacaran period. Despite all the challenges, climate change, atmospheric cataclysms, rising oxygen levels, volcanic eruptions, global glaciation, continental drift, sponges survived and continued to evolve. Even tectonic processes and the breakup of the supercontinent, Rodinia, could not halt the progress of life. It continued to evolve at incredible speed, laying the foundation for the next great era in the history of our planet, the Cambrian period, which would witness a veritable explosion of biological diversity. Although the Ediacaran period was not as rich and diverse as the period that followed, we can already see promising signs of a new world. The term Ediacaran itself comes from the Ediacara Hills in Australia, where unique fossils were discovered, including the oldest known complex multicellular organisms. The creatures we see here are strikingly different from anything that existed before. Their forms are beginning to vaguely resemble modern animals and plants, although they are still far from achieving the biodiversity we see today. The fauna of the Ediacaran period, which existed 635 million years ago, was astonishingly rich. Let's travel back in time. Dive into the warm, shallow seas off the coast of ancient Australia to see this lost world with our own eyes. What we see here will be unlike anything from previous eras. We owe this incredible discovery to geologist Reginald Sprigg. However, at that time, the scientific world was not yet ready to grasp the full significance of his find and its colossal impact on our knowledge of the prehistoric world. Imagine traveling back to 1946. Paleontologist Reginald Sprigg makes a discovery that will shake the scientific world to its foundations. Here, in the sun-baked Flinders Hills of southern Australia, in a place called Ediacara, he finds imprints of ancient jellyfish. These fossils were found in a geological layer that lay at the very boundary with the Cambrian period. Naturally, the initial reaction of the scientific community was predictable. These creatures must have lived during the Cambrian. But by the late 1940s, it became clear that this discovery had the potential to radically rewrite the entire history of life on our planet. The very idea that complex organisms could have existed long before the famous Cambrian Explosion seemed unthinkable, almost heretical. Almost a decade passed, and in 1957, half a world away, a new sensation thundered. In Great Britain, Charnia was discovered in the ancient rocks of Charnwood Forest. These fossils baffled scientists. On the one hand, they resembled life forms characteristic of Cambrian deposits, but on the other, their age clearly pointed to a much older pre-Cambrian era. This time, the question of the existence of complex life before the Cambrian was no longer a bold proposition, but a persistent scientific challenge. Surprisingly, the author of this epical discovery was not a renowned professor, but a 15-year-old teenager, Roger Mason. While walking with his friends along the rocky ledges of Charnwood Forest, his eye caught an unusual imprint on a stone. Boyish curiosity prompted him to take a simple action. He pressed paper to the stone and rubbed it with a pencil, creating an exact copy of the pattern. He showed this drawing to his father, who, recognizing the significance of the find, passed it on to geologist Trevor Ford. One can only imagine the emotional storm this discovery unleashed. For young Roger, it became a calling. He decided to dedicate his life to petrology, the science that studies rocks, their formation, and the transformations they undergo over the centuries. But let's return to 1957. Charnia's discovery was a true stumbling block, challenging established scientific dogma, although skepticism still hung in the air. The decisive blow to the old theory came in 1959. With the advent of more accurate radiometric dating methods, another eminent paleontologist, Martin Glessner, who devoted himself to studying Australian geology, was able to connect the disparate finds. He convincingly demonstrated that the creatures found in England and other enigmatic organisms from Australia, and even from the Canadian island of Newfoundland, belonged to the same era. And that era was the Precambrian. There was no longer any doubt. Martin Glessner devoted much of his scientific career to exploring this lost world, delving into the mysteries of the Precambrian oceans and their amazing fauna. His work is a window into an incredible, fascinating, and instructive past that helps us today understand the very origins of life and the great drama of evolution. The first thing that strikes the imagination when looking at these creatures is their bilateral symmetry, a trait we are accustomed to seeing in later animals, and the diversity of form is simply stunning. A veritable underwater garden unfolds before us, populated by outlandish creatures. Some resemble feathers, others tubes, and still others the bizarre leaves that carpet the seafloor. In this kaleidoscope of forms, one can even recognize familiar outlines reminiscent of jellyfish or corals. This was an undeniable fact. We were no longer dealing with primitive bacterial mats or microscopic algae. No, before us were organisms that, although unlike anything in modern fauna, had already reached an incredibly high level of complexity. Take, for example, Dickinsonia. This creature had an oval, flattened body with a clearly defined central axis, resembling a dorsal ridge. About 10 centimeters long, it resembled either a giant feather or an elongated leaf pressed tightly to the seafloor. Without a doubt, this was one of the most distinctive representatives of the species Dickinsonia costata. Dickinsonia. Hundreds of millions of years have passed since these creatures disappeared from the face of the Earth. Finding anything about their biology in their fossilized remains is a nearly impossible task. But some researchers, like Ilya Bobrovsky, had incredible luck. While working as a graduate student at the Australian National University, he conducted a detailed chemical analysis of one of the remarkably preserved specimens. And the results were stunning. Traces of cholesterol, a complex organic substance, were found in the fossil. This was the key to the mystery. Cholesterol is an integral part of animal cells. It's a fat molecule. The discovery was a real breakthrough, as it proved that Dickinsonia was an animal. The fact that this creature had exclusively soft tissue, without bones or shells, greatly complicates its study. But thanks to several unique fossils, including those discovered during Ilya Bobrovsky's excavations, we have been able to learn astonishing details. It turns out that Dickinsonia could grow to gigantic sizes, almost 1.5 meters in length, comparable to the height of a human. Yet, its flat body was no more than a few millimeters thick. This creature had neither a mouth nor a digestive system as we know it. It was firmly attached to the seafloor. Scientists speculate that Dickinsonia was a bottom dweller that absorbed nutrients, likely bacterial films, through its entire body surface. It grew by simply adding new segments, allowing it to increase in size over time. Dickinsonia's body was pierced by thin ribs radiating from the center to the edges. The species, Dickinsonia costata, was distinguished by its large, almost round outline, while other species, such as Dickinsonia tenuis, were more elongated and truly resembled a feather. All Dickinsonia belong to a large group of extinct animals called Proarticulata, which also includes creatures such as Yorgia and Archaeospinus. Proarticulata were the first truly bilaterally symmetrical animals on the planet. This evolutionary milestone is incredibly fascinating to observe. Just imagine, after billions of years of dominance by bacteria and microscopic algae, complex organized organisms with clearly symmetrical bodies appear on the stage of life. Many of them, like Dickinsonia, had a similar morphology, as if covered in feathers or leaves. The most striking example is the already familiar Charnia. Its sizes ranged from a modest 15 centimeters to an impressive 2 meters. This vast family of rancomorphs also includes such a species as Swartpuntia. All of them are an integral part of the enigmatic ecosystem of Vendobionts, a group uniting all these extinct creatures that inhabited the oceans during the Ediacaran period. When speaking of the Ediacaran fauna, we often use another term, Vendozoa. Vendobionts represent an entire layer of life whose origin and relationship to modern animals are still the subject of fierce debate. They seem similar to each other, but at the same time, they are infinitely distant from everything we know today. The fossil remains of these creatures, miraculously preserved through the abyss of time, are incredibly difficult to interpret. This is precisely why scientists have classified them as a unique, distinct group. Let's continue our dive into the depths of the prehistoric ocean to meet another species that is strikingly different from its neighbors. This is Tribrachidium. Its shape is a triumph of triradiate symmetry. 3 petals twist in a whimsical spiral around curved edges, creating a pattern resembling a strange rosette. This organism was small, only up to 5 centimeters in diameter, making it a rather modest inhabitant of the seafloor. Tribrachidium fed by filtering water through itself. It directed the currents toward the top of its cone-shaped body, and this movement created small eddies in the water, traces of which can sometimes be found in the surrounding sediments. Another bottom-feeding organism was Charniodiscus. This organism led a completely sedentary lifestyle, firmly anchored to the sandy bottom and never moving. Paleontologists distinguished 2 main groups of Charniodiscus. Some had short stems and wide leaf-like structures, while others had long stems and short leaves. These include species such as Charniodiscus arboreus, Charniodiscus longus, and Charniodiscus spinosus. The most striking thing about Charniodiscus is that it was a eukaryote, meaning its cells already had a membrane-protected nucleus, a sign of a high level of organization. Furthermore, its fossils are so well preserved that we can distinguish individual body parts. We see the so-called crampon, a root-like structure that allowed the animal to firmly attach to the substrate. We see a stem and branches resembling fern fronds. In some prints, these body parts are so clearly separated from each other that it's easy to imagine what this amazing organism looked like in life. The classification of Charniodiscus is a real headache for paleontologists. Initially, it was considered a rancomorph. Then, new classes were proposed, such as arboreomorphs and frondomorphs. It was even considered a cnidarian, or more specifically, a sea pen. And while its exact place on the tree of life is still actively debated, one thing is certain: it was an incredibly successful life form. Charniodiscus managed to spread to every corner of the globe. Its remains have been found from Australia and Japan to the Netherlands, from Charnwood Forest in England to distant Canada. Let me also introduce you to Sprigina. This amazing creature is named after its discoverer, Reginald Sprigg, whose name we've already mentioned. Sprigina represents an entirely different type of organism. The traces it left behind are so confusing that scientists have had serious difficulty classifying it. Was it a segmented worm, a fragment of fern, another ranomorph, or perhaps part of a Charniodiscus? We can clearly see Sprigina's head shield, called the cephalon. It is formed by the fusion of the first 2 body segments. Behind the head follows a long, segmented torso. Scientists speculate that it was a bottom-dwelling animal crawling along the seafloor in search of food. Our research leads us to the genus Rangia, an enigmatic creature from the Ediacaran family. This unusual organism possessed a complex fractal morphology. Rangia, also known as the elegant feather, was a kind of underwater plant, reaching a height of about 20 centimeters. It had bilateral symmetry, and its body was organized into branching structures similar to aloe leaves. These leaves, folded and arranged in a strict geometric pattern, appeared to be perfectly designed to maximize nutrient absorption from the surrounding water. Due to its root-like structure, or crampon, Rangia likely lived near the seafloor. However, it remains a mystery whether it was an autotrophic organism, that is, whether it could, like plants, capture light energy, perhaps through symbiosis with microorganisms. This lost world still holds its secrets. It may have fed by filtering water through itself, filtering out tiny food particles suspended in the water column. Its very body structure is direct evidence that it was born to live in shallow, warm, sunlit waters, where nutrients and light were abundant. This is precisely what makes Rangia a key figure in the survival drama of that era. It likely stood at the very center of the first complex food chains that were just beginning to emerge in the ocean. Now, let's travel to ancient Australia, where paleontologists have discovered another astonishing member of that fauna, a creature called Arkarua. Imagine a creature no bigger than a pea, just 5 millimeters across, yet it opens a window into a completely different world. Arkarua had 5 axes of symmetry, just like modern starfish, whose distant ancestor it may be. Externally, it resembled a tiny disc-shaped coin with a pattern of 5 rays radiating from a small depression in the center. Its exact role in the ecosystem remains a matter of debate, but it was likely a bottom dweller, slowly crawling through the mud, devouring organic remains. Its mineralized shell, a kind of primitive armor, may have served as protection, and not only from the vagaries of the elements, but also from the first predators that had already begun their bloody hunt in these ancient seas. Studying creatures like the Arkarua helps scientists understand how and when complex, symmetrical body shapes emerged in the animal kingdom. Let's move on to another, no less impressive and mysterious inhabitant of the Ediacaran seas, Yorgia. This creature, reaching 1/4 meter in length, roughly the size of a large man's shoe, had a flat, segmented body resembling a fallen leaf. Rows of elongated plates ran along either side of its midline. This complex bilateral symmetry hints that Yorgia led a much more active life than its neighbors. Indeed, unlike many other sedentary organisms of the time, Yorgia left behind irrefutable evidence, fossil footprints. This means it was capable of movement. Albeit slowly, it moved along the sea floor. These fossilized tracks, known to paleontologists, demonstrate a smooth, purposeful gliding motion. Yorgia wasn't simply drifting, it was actively searching for food. It likely crawled slowly, scraping nutritious mats of bacteria from the bottom, the ultimate delicacy of the time. Thanks to its complex structure and ability to move, Yorgia became a crucial milestone in evolution, demonstrating how multicellular life takes its first steps toward more active and specialized forms. Now, let's look at something completely different. A remarkable organism appeared in the Ediacaran fauna, revolutionizing the world by developing a hard skeleton. Its appearance forever changed the face of the ocean, as it became the builder of the very first reefs on the planet. While we can appreciate its colossal role in history, imagining what it actually looked like is incredibly difficult. This pioneer's name is Cloudina. Why is it so important to dwell on this creature in our journey into the past? The fact is that Claudines constructed gigantic reef structures hundreds of millions of years before corals came onto the scene. Yes, today, when we hear the word reef, we immediately imagine vibrant coral gardens. But back then, in ancient times, the role of chief marine architect belonged not to corals, but to these enigmatic creatures. One of the most famous testimonies to their titanic work is the fossils discovered in Namibia. They are estimated to be 542 million years old. Imagine the amazement of the scientists from the Nama group when they made this discovery. Amazingly, the remains of this ancient underwater metropolis today lie in one of the driest deserts on the planet, where there is not a single drop of water for hundreds of kilometers. But Claudine wasn't building alone. If you look closely at these ancient structures, you'll recognize the familiar outlines of stromatolites, those same stone formations we've already seen created by colonies of bacteria. But this time, our attention is focused not on them, but on the work of the planet's first reef builder. British and Namibian geologists made a truly incredible discovery in the deserts of Namibia. They witnessed firsthand the process of biomineralization, when a living organism creates minerals. This was one of the first creatures to learn to create a hard shell for itself. This discovery marked a monumental milestone in the history of life, the boundary between the age of defenseless, soft-bodied creatures and a new era of animals capable of protecting themselves with armor. With the emergence of the first reefs, the ocean began to take on a completely new appearance. Here we see creatures radically different from anything that had come before. The development of a hard shell in these organisms became the impetus for an explosion of biodiversity and the emergence of increasingly complex life forms. This creature received its name, Cloudina, in honor of geologist and paleontologist Preston Cloud, who first studied it. From early research, we know that Cloudina was one of the first so-called armored metazoans, multicellular animals with armor. It was small. The fossils it left behind are microscopic fossils consisting of nested limestone cones. These cones are only a few millimeters in diameter, and their length ranged from 8 to 150 millimeters. Cloudina lived in huge colonies, adhering to each other and to any hard surface. They created a kind of natural cement that formed massive and strong reef structures. Many scientists have attempted to unravel the mysteries of these ancient ocean dwellers. But it was Professor Rachel Wood and her team from the University of Edinburgh and the Geological Institute of Namibia who were able to shed light on Cloudina and her colossal significance for the ocean. Just as today, reefs played a vital role in marine life. They were an entire ecosystem that provided refuge from predators for countless species. For some, the reef was a fortress. For others, a food source or a symbiotic relationship, greatly increasing their chances of survival. But one question about Cloudina remains unanswered. Every evolutionary leap is a response to a challenge. It is an adaptation to climate change, environmental change, or the emergence of a new threat in the form of predators. So, Cloudina's hard shell and reef-building ability were undoubtedly such an adaptation. But to what exactly? What compelled this creature to take such a revolutionary step? One thing is certain. Cloudina unwittingly became a cradle for the emergence of new, far more complex life. In future eras, we will see the descendants of these first protected creatures grow, develop, give rise to new species, and achieve incredible evolutionary breakthroughs. If we were to summarize this incredible journey into the past, we would begin with the fact that Earth was already habitable 1 billion years ago. Contrary to what might appear, it was not a dead world. Life was modest, but it was there. It was a world at once mysterious and in a state of constant change. The Precambrian, and especially the Neoproterozoic Era, provided the fertile soil in which the seeds of future biodiversity sprouted. It was a turning point in the history of our planet. The profound geological and biological transformations of that period became the prelude to the great drama of evolution. 1 billion years is practically yesterday in geological time, but traces of those events are still visible in the rocks and fossils we study today. Although life was only just beginning its journey then, already in the Neoproterozoic, it was undergoing radical changes that would shape the future of the entire planet. One need only glance at the kaleidoscope of climatic, geological, and biological events that raged during that era. More than 1 billion years ago, the Earth was unrecognizable. The Neoproterozoic period witnessed global glaciations, the formation and breakup of supercontinents, violent volcanic eruptions, the birth of new species, and, most importantly, the emergence of oxygen. It was oxygen that played a key role in the formation of the ozone layer, Earth's protective shield, and forever changed the rules of the game for the first ocean dwellers. It's astonishing the metamorphoses that have occurred in just a few 100 million years. Whereas previously, life was represented primarily by bacteria and algae, we now see the oceans brimming with a diversity of multicellular organisms. These creatures take on the most bizarre forms, some of which resemble feathers. Animals with bilateral symmetry appear, something never seen before. The first creatures with hard shells are born, giving impetus to the development of other species and the formation of the world's first multicellular reefs. These events marked the final chords of the Precambrian period and opened the door to the next great era, the Phanerozoic. This entire historical period was merely an overture to the great Cambrian explosion of life, which we will definitely discuss later. But what did the planet look like at that moment, at the dawn of the Cambrian period, which marks the beginning of the lower Paleozoic? In the Precambrian era, there existed a gigantic supercontinent, Rodinia, which encompassed almost all of the world's landmass. But under the influence of inexorable tectonic forces, it began to crack at the seams and gradually disintegrate. Huge chunks of continental crust began to float freely across the vast oceans. And so, shortly before the beginning of the Cambrian, 2 new continents formed on Earth. The larger one was named Laurentia. and it became the core around which much of modern North America would later form. Let's travel back in time, hundreds of millions of years ago, when the face of our planet was completely unrecognizable. In those distant times, the continents we are familiar with did not exist. In their place, there were gigantic landmasses whose outlines only vaguely resembled the future continents. One of these supercontinents, known as Laurentia, already contained the seeds of North America, but without the territories that would one day become Florida, Greenland, and Scotland. The second, slightly smaller continent formed the foundation of what would become Siberia, the so-called Siberian Shield. Then, at the dawn of the Cambrian period, a third colossal fragment, which paleontologists would call Baltica, broke away from the giant continent of Rodinia. It was from this landmass that the territories of modern-day Russia, Poland, Scandinavia, and northern Germany would eventually form. The shattered remnant of Rodinia, this gigantic progenitor continent, was given a new name, Gondwana. But even stripped of its parts, it remained colossal, encompassing what would become South America, Africa, Australia, the Antarctic ice cap, southern Europe, and even the lands of China. And so, when three new gigantic landmasses emerged on the planet, Laurentia, Siberia, and Baltica, they immediately fell under the grip of the inexorable forces of plate tectonics. These colossal sections of the Earth's crust began to move, beginning their slow, multi-million-year dance. They converged and diverged, like giant ships on a boundless ocean. As a result of this great shift, some oceans were born, while others, conversely, were doomed to disappear. Between Laurentia and Gondwana, at the site of a gigantic rift in the breakup of Rodinia, a new ocean, known to us as Iapetus, emerged. Millions upon millions of years later, this ancient ocean slowly but surely expanded its boundaries in the southern hemisphere. This was due to ocean floor spreading, fueled by the mid-ocean ridge, a gigantic underwater scar that ejected new crust and pushed the continents apart. However, approximately 50 million years after its birth, at the end of the Cambrian period, the fate of the Iapetus Ocean began to change. Planetary forces triggered a reversal that would destroy this watery world. A subduction zone emerged in southern Laurentia, a place where one oceanic plate began to slowly but inexorably dive beneath another. This titanic process gave birth to a chain of volcanic islands, a veritable arc of fire rising from the depths. Volcanic emissions from these islands mixed with the gigantic masses of sand and mud that were already accumulating in the space between the continent and this new archipelago. Tons of sediment began to accumulate in this zone, and eventually the Iapetus Ocean began to slowly close, like a giant vice. This process took about 20 million years. Moreover, smaller continental blocks were breaking away from the Great Gondwana, also rushing north. All these events combined sealed the ocean's fate. When Laurentia finally approached the edge of this volcanic archipelago, the inevitable occurred: a collision. This was a planetary-scale catastrophe, marking the beginning of a long and arduous process of the birth of new mountains. Thus began the Great Caledonian Orogeny, an era of mountain building that laid the foundations of the future Appalachians in North America and created the mountain systems of Scotland and Scandinavia. The Cambrian period began with a monumental event, the end of the last great ice age in Earth's history, marking the end of the Proterozoic Era. Glaciers retreated, and global warming led to a significant increase in average temperatures, even higher than we observe today. But was the land born in this tectonic throes ready to host life? Although the climate seemed paradisiacal, with an average global temperature of about 25 degrees Celsius, 77 degrees Fahrenheit, the continents clustered around the equator were a dead, lifeless desert. Unlike the oceans, there was no life here. And tiny cyanobacteria played a key role in this. They gave rise to the first algae, which began to saturate the atmosphere and oceans with oxygen, opening entirely new horizons for evolution. while Laurentia, Siberia, and Baltica enjoyed a tropical climate, the giant Gondwana, located closer to the polar zone, suffered from low temperatures, but its surface was still devoid of any soil cover. In the tropical zone, conditions seemed more favorable. The atmosphere already contained about 20% oxygen and 0.5% carbon dioxide. However, an invisible but deadly threat existed. The ozone layer, our main protector, was still too thin to shield the surface from the sun's deadly ultraviolet radiation. This deadly radiation literally sterilized the land, making it completely uninhabitable. Without a single sprout, without a hint of vegetation, the planet's surface resembled a Martian landscape. Endless, parched, cracked plains, and bare, rocky peaks, subject to relentless erosion. But the shallow oceans, with their warm, sun-baked waters, became a true cradle of life. Here, protected by the water column, favorable conditions allowed evolution to take giant strides forward. From the very beginning of the period, the underwater world was populated first by single-celled organisms and then by the first multicellular organisms. Prokaryotes, single-celled microorganisms without a nucleus, such as bacteria and archaea, already existed in those distant times. Cyanobacteria, or blue-green algae, which appeared in the Proterozoic, also flourished alongside them. It was precisely the climate and chemistry of the oceans that played a decisive role in the subsequent fate of these species over the 56 million years of the Cambrian period. But before this great breakthrough, there was a mysterious prelude. Toward the end of the Proterozoic era, about 600 million years ago, the so-called Ediacaran fauna appeared in the oceans. These were strange soft-bodied creatures resembling leaves, discs, or tubes. They flourished for nearly 56 million years, but then, as suddenly as they appeared, they disappeared. The cause of their extinction remains one of the greatest mysteries of paleontology. Traces of these primitive organisms, which included the ancestors of jellyfish, corals, segmented worms, and arthropods, are found all over the world, but their story was cut short. And then, after the Great Dying, something incredible began. The Cambrian period was a game-changer, ushering in the fossil record as we know it. As the glaciers retreated, the planet was transformed. Temperatures became milder and sea levels rose, inundating the edges of continents and creating vast, shallow, epicontinental seas. This became the perfect breeding ground for underwater life, which exploded with unprecedented diversity. But it wasn't just a matter of quantity. In a geologically insignificant period of time, such a staggering diversity of new anatomical forms appeared in the oceans that this event has gone down in history as the Cambrian Explosion. It wasn't just a step in evolution, it was a gigantic leap, a true biological Big Bang. Some scientists even call it the Great Zoological Breakthrough. It was during this period, between 540 and 505 million years ago, that most modern animal phyla emerged. Life seemed to go wild, experimenting with shapes and sizes. For the first time in the planet's history, living organisms began to grow hard parts, shells, carapaces, and even the first primitive skeletons. It was these that left countless traces in the fossil record. Most of them, of course, were soft-bodied creatures like worms and sponges. But along with them, the first arthropods also appeared, the distant ancestors of modern crabs, spiders, and insects. The ancestors of cephalopods, such as octopuses, also appeared. This rapid emergence of new species, especially those with bilateral body symmetry, incredibly complicated ecosystems. They became incomparably richer than those that existed in the Ediacaran period. At this point, entirely new ecological interactions emerged in the world's oceans, the most important of which was predation. Some benthic creatures adapted to living on the seafloor or burrowing into the mud. Others, tectonic, mastered the water column, becoming active swimmers. What triggered this evolutionary fireworks display? Scientists are still puzzled, but several hypotheses exist. One of the leading theories points to a sharp increase in dissolved oxygen levels in the world's oceans after the end of the Ice Age. It's also possible that the waters became saturated with phosphates and nitrates, key elements for photosynthesis. This spurred the development of phytoplankton, the base of the food chain, and provided organisms with the building blocks for shells and carapaces. But the most captivating theory is the beginning of the planet's first arms race. The emergence of predators generated incredible evolutionary pressure. To survive, their prey was forced to develop new, increasingly sophisticated defenses, durable shells, sharp spines, and the ability to burrow into the ground. In response, predators became even more deadly, developing jaws, claws, and even the first eyes, which provided a huge advantage in hunting. A reasonable question arises: how can we, hundreds of millions of years later, judge these microscopic dramas that played out on the floor of an ancient sea? After all, finding fossilized remains of dinosaurs that lived 300 million years later is no easy task, let alone these tiny creatures. Fortunately for paleontologists, vast tracts of the seafloor of that very same Iapetus Ocean did not vanish without a trace. During the continuous movement of tectonic plates, which crushed the Earth's crust into gigantic folds, the former ocean floor was uplifted to incredible heights, becoming part of great mountain ranges. And this incredible explosion of life left behind countless fossils, which can today be found high in the mountains, where the waves of the ancient Cambrian Sea once lapped. Evidence of this era, the Cambrian period, is not confined to one corner of the planet. No, their imprints are scattered across the globe, their legacy inscribed in the rock record of every continent. Imagine that our entire understanding of this lost world is a mosaic assembled from miraculously surviving fragments of the past. To this day, paleontologists, like time detectives, continue their search in these unique places, trying to find the missing pieces of this grandiose picture. Let's move on to France, where the Cambrian era has left an equally vivid mark. From the southwestern slopes of the Massif Central, particularly in the Montagne Noire, to the rugged Pyrenees and the coast of Normandy, stone everywhere holds the secrets of ancient life. It was in the Montagne Noire that a landmark discovery was made back in 1888, the first trilobite fossils in France, creatures that once ruled the seafloor. Stratigraphy, or the sequence of layers in this region, has proven a true gift for scientists, revealing the history of the Cambrian in exquisite detail. But there's one place that has become a true treasure trove, a window into the Cambrian world. It's the Burgess Shale. Let's go back to August 30th, 1909. A paleontologist named Charles Doolittle Walcott is trekking through the wild Canadian Rockies into the heart of Yoho National Park. Little does he know, he's about to make one of the greatest discoveries in the history of paleontology. Here, at the foot of Mount Burgess, he finds rock strata containing fossils dating back more than 500 million years. It was practically the end of the Cambrian period. Slate is a remarkable rock formed from compressed clay and silt. Layer by layer, millimeter by millimeter, it holds history. And when these layers split, they reveal incredible, sometimes downright fantastical, fossils, like pages of a stone book. To understand how these treasures were preserved, one must imagine a scene that occurred 500 million years ago. Where inaccessible mountains tower today, the ancient Iapetus Ocean once lapped, and then a gigantic torrent of liquid mud bursts from an underwater ledge. It rushes along the seafloor, burying all life beneath it. For the bottom dwellers, this was an instant catastrophe. But for science, it was a true miracle. In this oxygen-deprived tomb, decomposition slowed almost to a halt, and over time, under the pressure of the thick rock, these creatures turned into thin, jet-black imprints, ghosts of a distant past. Typically, Cambrian deposits yield only tiny skeletal fragments, the remains of what's known as small shell fauna. Scientists study these mineralized particles, sclerites, which formed part of the tissues of ancient corals, spicules, the hard needles that made up the skeletons of sponges, microscopic tubes and shells. All of these are disparate parts belonging to many different species. But the Burgess fauna is something entirely different. Here, we uncovered not just skeletons, but entire organisms. For the first time, scientists saw not just shells, but also soft tissue, legs, eyes, mouthparts, digestive tracts, antennae, and a host of other details that usually disappear without a trace. To date, approximately 150 species of ancient animals, algae, and even bacteria have been identified in the quarry established by Walcott alone. Thousands upon thousands of specimens collected into vast collections have allowed researchers to glimpse an entire ecosystem of the ancient world for the first time. Such an abundance of material made it possible to apply statistics, and the numbers astonished everyone. Almost 98% of all fossils found belong to organisms without a hard skeleton. It's these unique preservation conditions that make the Burgess Shale a global treasure. Most other Cambrian deposits around the world simply lack such fossils. Not because there weren't soft-bodied creatures there, they were everywhere, but because the conditions for their preservation weren't there. The Burgess community is first and foremost a world of animals. Of course, traces of plants have been found here, several species of green and red algae, and even entire colonies of ancient microbes. But the main players in this new habitat were, without a doubt, arthropods, small creatures with jointed limbs that busily crawled along the bottom, as well as the porous organisms we know as sponges. So, let's dive into the waters of the Iapetus Paleocene and take a look at the creatures that inhabited our planet in those distant times. Let's start with the most numerous inhabitants, those who spent their lives on or near the seafloor. Here, right before us, scurrying through the mud, is a small but very important creature, Canodaspis perfecta. It is one of the ancestors of all modern arthropods, from crabs and shrimp to insects and spiders. No larger than a finger, its body protected by a tough carapace, ending in a segmented tail tipped with a pair of sharp spines. Look at its head, a pair of beady eyes, and between them, like a miniature spine. Two pairs of antennae constantly probed the surrounding area. The short ones were for touch, and the long ones likely detected scents in the water, helping it find food. Its head bore 6 pairs of limbs, topped with sharp claws. Its torso consisted of more than a dozen segments, and on the thorax we see 8 more pairs of legs, also with claws. But the rear part of the abdomen was completely smooth, without limbs. This creature's legs were versatile tools. They served both for locomotion and as gills for respiration. Canodaspis perfecta spent its entire life wandering along the seafloor, stirring up the silt with its numerous legs in search of edible particles. Once food was found, its powerful mandibles would spring into action to grind it up and swallow it. Among the bottom dwellers were numerous creatures with elongated bodies, very similar to modern worms. They either crawled along the seafloor or burrowed into soft sediments. Some species, with their unique body shape, could even actively swim. These elongated animals are classified as annelids, and as many as 5 species have been found in the Burgess Shale. Among them are Piranha, which preferred life in the sedimentary rock, and Canadia spinosa, which floated freely on ocean currents. Let's take a closer look at Canadia spinosa. This unique worm averaged 3 centimeters in length, with the largest specimens growing up to 4.5. But its most distinctive feature was the dense, stiff bristles covering its entire back. This is a distinctive feature of polychaete worms. Their segmented bodies are equipped with lateral appendages, called parapodia, which serve for locomotion. These parapodia bear tufts of bristles that help them paddle through the water. And here's its relative, Peronopsis. This tiny thread-like worm gets its name from the Greek words peron, meaning needle, and keith, meaning long hair, which perfectly describes its appearance. It's only 1 to 2 centimeters long and no more than 1 millimeter wide. Its body consists of about 25 segments, each with a pair of parapodia. It was a predator, albeit a tiny one. A simple intestine ran through its entire body, and a pair of sensitive tentacles were located on its head. Peronopsis was a generalist. It could both crawl along the surface of sediments and burrow deeper. Its setae were the perfect tool for quickly burrowing into the mud in search of prey or escaping danger. But the amazing fauna of Burgess Island also included a much larger worm, a true superpredator of the Cambrian period. Meet Otoya prolifica, a creature many would call a monster. It grew up to 11 centimeters, and its broad head was armed with 50 razor-sharp hooks. Its arrow-shaped form earned it the nickname arrowworm. These numerous, flexible hooks allowed it to seize any prey with a death grip. This worm is rightfully considered one of the most dangerous marine predators of its era. Amazingly, its descendants still live in every sea in the world today. True, they are now only a few millimeters long. But even as a tiny part of the plankton, they behave like ferocious predators, terrifying young fish and small crustaceans. The seafloor was also home to brachiopods, animals that may well have been prey for this worm. These organisms fed on suspended particles in the water, and their bodies were enclosed in a double-valved shell. They typically attached themselves to the seafloor or to other, larger creatures using a flexible foot-like organ. One such brachiopod was Micromitra burgessensis, which reached no more than 10 millimeters in length. Its name translates from Greek as little turban. It was the most ornate brachiopod found at Burgess. Its mineralized shell was covered with pronounced growth lines and thin, textured ribs that radiated from the hinge across the entire surface, creating an elegant, diamond-shaped pattern. The valves were semicircular, and the hinge was almost perfectly straight. But the most striking feature of this creature were the long, thin setae that extended far beyond the edges of the shell, like eyelashes. Besides all these bottom dwellers, other animals were also actively swimming in the ancient ocean. Particularly interesting are the chordates, creatures that already possessed a dorsal cord and neural tube, the precursors of the future spine. Among them, Pikaia stands out, a fossil from the Burgess Shale, undoubtedly the most primitive form of chordate known at the time. Before us is the distant ancestor of all vertebrates, including us. Let's travel to the bottom of the ancient ocean, where an amazing story of life unfolds. Here, in the depths of the silt, lived a creature that outwardly resembled a common worm. However, this modest appearance concealed a true evolutionary breakthrough. It already possessed myomeres, muscle fibers that are the hallmark of vertebrates. This tiny creature barely reached 5 centimeters in length, and its elongated body with a clearly defined head made it resemble a miniature eel. Its sides were flattened, suggesting the presence of a primitive pelvic fin at the rear of its body. This creature may not look impressive to science, but it left an indelible mark on the great annals of evolution, becoming one of the ancestors of all future vertebrates. The seafloor at that time was a veritable arena for survival. Countless organisms scoured the waters for food, sifting through the mud or swimming in pursuit of organic particles, hunting for ancient snails and sea urchins. Among these hunters, one particularly remarkable arthropod predator stood out, known to paleontologists as Sydneyaia. Imagine this creature. Its maximum length reached 160 millimeters, comparable to the size of an adult human palm. Its body was protected by a convex head shield, short but very wide, almost rectangular in shape. The sides of this shell had special notches for long antennae, and small ears were located at the edges. From above, like two spotlights, shone two hemispherical, highly reflective eyes set close together. The thorax of this predator consisted of 9 segments, with the central one noticeably wider than the others. The first 4 pairs of forelimbs were powerful, with a wide base, while the remaining 8 were more graceful and ended in a needle-sharp claw. The next 5 segments of its body bore completely different appendages. They were connected by bundles of fine threads, which together formed something resembling a whimsical wing. This predator's body ended with an abdomen composed of 3 slender segments, at the end of which was a triangular telson. This tail was adorned with 2 enormous lobes, which, when brought together, formed a powerful fan. The 4 front pairs of limbs served this animal both for swimming and for moving along the seafloor, like a multi-purpose tool. The 5 rear pairs of thread-like appendages, however, generated thrust, allowing it to maneuver through the water. It's quite possible that these same threads also served as respiratory organs, acting like primitive gills. The spiny projections at the base of the head helped this creature grind up its prey and force it directly into its mouth. Its sensitive antennae and keen eyes constantly scanned the space, searching for prey, which it would seize and mercilessly crush with its forelimbs. But if Sydney seems strange to you, then prepare to see something completely alien. Meet another primitive arthropod that defied all expectations. Opabinia regalis. This creature had not 2, but 5 eyes. Its incredible morphology, including the bizarre proboscis on the front of its head, made it a true mystery to scientists for many years. This proboscis is one of the most recognizable features of the entire Burgess Shale fauna. Opabinia's body reached just over 10 centimeters in length and was equipped with gills and lateral lobes that rhythmically repeated along the entire body, ending in a large tail fan. Not counting the proboscis, the body itself was 4 to 7 centimeters long. On the front of the rounded head were 5 bulging eyes, topped with short tentacles. And in front of them was the famous proboscis, flexible, ringed, 4 times longer than the head itself. It ended in a pair of powerful pincers, each bearing 5 or 6 sharp spines. The mouth of this creature was located at the bottom and directed backward. The body consisted of 15 segments, each bearing a pair of lateral lobes with gill plates. Following this creature was another fantastical sea creature, resembling a living fan with 3 pairs of fins pointing upward. This predator glided through the water thanks to the undulating movements of its lateral blades, which acted like propellers. Its long tail fan served as a rudder, allowing it to maneuver confidently through the water. Its flexible proboscis and a pair of deadly pincers were ideal for capturing soft-bodied prey and delivering it directly to its mouth. Undoubtedly, the seafloor of those times was literally strewn with echinoderms, a unique group of organisms with mineralized skeletons. Their bodies were composed of numerous elements arranged in a 5-armed symmetry. Today, we see this same structure in starfish, whose bodies are composed of 5 identical parts radiating from a central core. These ancient predators apparently consumed mollusks in enormous quantities. Of the 5 species found in the Burgess Shale, only one, Scanella, had a complete mineralized shell. Sponges, some of the most primitive multicellular animals on the planet, were also an integral part of the ocean floor. Their bodies lacked true tissue, but instead had a skeleton made of a network of fine mineral needles known as spicules. These amazing creatures were bottom-dwelling filter feeders, filtering water and nutrient particles. Specimens of several species of sponges from the genus Vauxia, including Vauxia gracilenta, have been found in the Burgess Shale. This sponge, very common in that ecosystem, reached a length of up to 8 centimeters. It could be simple and unbranched or form complex branched colonies. Each branch was nearly cylindrical, forming a pointed cone with a central cavity. To survive, these creatures had to continuously force water through channels in their walls, trapping organic particles. Other species, differing in skeletal structure and branch shape, such as Vauxia bullata and Vauxia densa, were also widespread. These species could reach 15 centimeters in diameter, forming veritable underwater thickets, ideal shelter for small benthic fauna. However, the most famous sponge from the Burgess Shale is undoubtedly Hazelia palmata. It belongs to an advanced group of sponges. The genus Hazelia was distinguished by a huge variety of forms. Some species were large and cup-shaped, others elongated and conical, and still others highly branched. Despite the colossal differences in appearance, all these species had a similar microstructure. Thin walls composed of small spicules tightly woven into a mesh-like structure. Hazelia palmata is particularly notable, reaching 15 centimeters in length. It was distinguished by an open, shield-shaped form and numerous clusters of protruding spicules. Among the arthropods that inhabited the seafloor alongside these sponges, Naraoya, stands out, often compared to trilobites. This marine animal, no more than 4 centimeters long, possessed 2 ovoid dorsal scutes. One scute covered the head, while the second, elongated one, protected the rest of the body. 2 long, sensitive antennae protruded from beneath the anterior scute. Behind them were numerous segmented appendages. This animal had 2 pairs of head appendages and another 14 pairs on the body. Each of these appendages was forked. One branch, segmented and powerful, was ideally suited for walking along the bottom. The other was a bundle of fine threads that likely served as gills. Thanks to its antennae, which likely served as tactile organs, Naroya could locate food and bring it to its mouth using a spiny plate at the base of one of its limbs. If necessary, this animal could perform short swims, using its thread-like gills to propel itself through the water. Although Naroya was a scavenger, or even a small predator, scars found on the shells of some specimens indicate that it was actively hunted by larger predators. Finally, rounding out our list is a tubular-shelled predator, Odorea alata. Most of its body was enclosed in a strong, tube-like framework with a distinct line running down its back. The framework was open front and back, providing the animal with reliable protection. Odorea's head, protruding from this tube, was adorned with a small anterior plate with large spherical eyes. Its body consisted of approximately 47 segments, each bearing a pair of appendages. The first 2 segments were modified into slender limbs adapted for locomotion. The remaining appendages were branched. The inner branch was powerful, while the outer branch bore thin plates. The tail consisted of 3 fins extending to the sides. Its tubular shell likely made it difficult for Odorea to move along the seafloor. Nevertheless, it was a very agile animal. It was able to confidently swim through the water thanks to the wave-like motion of its internal branches. Like a living suction tube, it filtered the water, absorbing small organisms along the way.